There is a crack running through the foundation of reality, and physics has spent a century pretending not to see it. Every prediction we make about the subatomic world is flawless. The equations never fail. And yet, hidden inside that perfection is a question so disturbing that some of the greatest minds who ever lived simply stopped asking it. The question is this: does anything out there truly exist in any fixed sense when no one is there to look at it? Begin with a single electron. Your intuition tells you it must be somewhere, a tiny speck sitting at a definite point in space. But quantum mechanics insists otherwise. Before you look, that electron does not occupy one position. It occupies all of them at once, smeared across space as a blur of overlapping possibilities. It is here and there, left and right, spinning up and spinning down, simultaneously. This is not ignorance about where it is. This is what it is. We capture this ghostly haze of possibility in a single mathematical object, the wave function, written with the Greek letter psi. The wave function is not a thing you can touch. It is a description of every possible state the system could be found in and how likely each one is. While no one observes it, psi spreads, ripples, and interferes with itself, like waves crossing a still pond. The particle, in a sense, is a wave. Then comes the act of looking and everything changes. The instant you measure the electron, the spread out wave does something violent. It collapses. All those overlapping possibilities vanish in an instant and the particle snaps into a single definite location. This is the heart of the Copenhagen interpretation, the orthodox creed of quantum physics. Reality is fuzzy and undecided until observed, and observation is what forces nature to choose. But here is the first tremor of unease. The Schrödinger equation, the master law governing the wave function, says nothing about collapse, nothing at all. It describes phi evolving smoothly, gently, deterministically forever. According to the mathematics itself, the wave should never snap. So where does the collapse come from? The equation does not predict it. We simply bolt it on by hand, because that is what we observe. A law for the world and an exception for the act of seeing it. And this forces a question that sounds almost childish, yet has no agreed answer. What counts as an observation? When we say a measurement collapses a wave, what physically performs that measurement? Is it the detector, the flash on the screen, the click of a Geiger counter, or does the collapse wait hovering until the result reaches a living eye? The theory that governs all of matter cannot tell us where measurement begins and the quantum world ends. The mathematician John von Neumann stared directly into this abyss. He realized something terrifying. A measuring device is not magic, it is made of atoms, and atoms obey the Schrödinger equation. So when your detector interacts with the electron, the detector should not collapse the wave. It should join it. The detector itself enters a superposition, pointing it up and down at once. The measurement has not ended the ambiguity. It has only spread the ambiguity into the machine. And it does not stop there. The screen you read is also atoms. The light bouncing off it is quantum. The photons entering your eye, the cells in your retina, the neurons firing in your brain, all of it governed by the same equation, all of it sliding into the superposition. The ambiguity climbs the chain link by link. Von Neumann was driven to a chilling conclusion. Perhaps the only thing that can finally break the chain is consciousness itself. Think about what that implies. If collapse requires a conscious mind, then mind is not a passenger in the universe, it is a trigger. The cosmos would remain an undecided fog of probability until awareness reaches in and pins it down. But this is a desperate solution, and physicists hated it. It smuggles the human soul into an equation about particles. It makes you the author of reality, and it raises an unbearable follow-up question. Where exactly is the line? A single atom is unmistakably quantum. A cat is unmistakably classical, either alive or dead, never both. Somewhere between the atom and the cat, the strangeness is supposed to switch off, but no one has ever found that threshold. There is no marker in the equations, no size at which superposition is forbidden. The boundary between the quantum and the everyday is not a law of nature. It is a place we stop looking. So we are left with a ghost in the device. The wave function refuses to collapse on its own. The measuring instrument only inherits the haze. The chain of uncertainty propagates upward, threatening to swallow detectors, laboratories, scientists, the whole world, unless something somewhere says enough. For decades this was treated as a philosophical curiosity, a puzzle for late-night arguments. Then, in 1961, one physicist designed a thought experiment that turned the puzzle into a nightmare. His name was Eugene Wigner, a Nobel laureate, and his scenario is deceptively simple. Imagine a friend sealed inside a perfectly isolated laboratory. Inside, the friend performs a quantum measurement, say, observing an electron that could be spin up or spin down. The friend looks at the result. For the friend, the wave collapses, the answer is now definite. It is, let us say, spin up, a clean, settled, undeniable fact. Inside that room, reality has made its choice. But now step outside with Wigner. From his vantage point, the laboratory is sealed. No light, no sound, no information leaks out. To Wigner, the lab is just an enormous quantum system that has not yet been observed by him. And the Schrödinger equation is unambiguous about what that means. Until Wigner opens the door, the entire contents of that room must continue evolving as an undisturbed wave function, uncollapsed, undecided, suspended in superposition. Follow that logic to its dreadful end. If the room is in superposition, then so is everything in it, including the friend from outside. Wigner must describe his colleague as existing in two states at once, a friend who saw spin up and a friend who saw spin down, entangled together, blurred into a single ghostly sum. The observer has become the observed. The one who collapsed the wave is to another, still smeared across both outcomes. Now hold both descriptions in your mind. The friend swears the outcome is fixed, a real, witnessed event that happened. Wigner insists the outcome is not yet decided, a superposition still waiting to collapse. These are not two opinions, they are two predictions, each derived correctly from the same physics, and they flatly contradict each other. One says a fact exists, the other says it does not, and nothing in the theory tells us which of them is wrong. This is where something precious quietly dies. We have always assumed that facts are universal, that if something happened, it happened for everyone, everywhere. Wigner's friend shatters that assumption. The measurement was a fact for the friend and a non-fact for Wigner. At the very same instant, reality, it seems, is not one shared stage. It may be relative to the observer, a private event, true in here and undecided out there. Objectivity itself is on trial. Faced with this horror, some physicists made a startling move. What if the problem is the collapse? What if the wave function never collapses at all? Not for a camera, not for a mind, not ever. This was a radical proposal of a young physicist named Hugh Everett in 1957. Take the Schrödinger equation completely literally. Let it run unbroken, with no exceptions, no magic moment of snapping. Follow it to the end and see where it leads. If there is no collapse, then the superposition never disappears. When the friend measures spin up and spin down, both outcomes remain real. The friend does not choose one, the friend becomes both. There is now a version who saw up and a version who saw down, each fully conscious, each convinced the result was singular. Neither is an illusion, neither is the true one. The equation never deleted a possibility, it simply kept all of them. This is a many worlds interpretation, and its central image is staggering. Reality does not collapse, it branches. Every quantum event with multiple outcomes splits the universe into parallel copies, one for each possibility, all equally real, forever diverging and never meeting again. You are branching constantly billions of times a second into uncountable versions of yourself. There is no contradiction in Wigner's friend, because there is no single outcome to disagree about. In one branch, the electron was measured spin down, and there exists a complete world, a friend, a laboratory, a Wigner, who will only ever know that result. The quantum mathematics still assigns it a weight, a probability, perhaps 35%. But within that branch, the inhabitants do not feel like a fraction. To them, it simply happened. Their world is whole. The probability is not a chance of existing. It is the sickness of a reality already real. In parallel branch, the heavier one, weighted at 65%, The electron was spin up. A different friend, equally certain, equally alive, inhabits that world and will never suspect the other exists. Wigner and his friend never truly disagreed. They were simply standing in different branches of an endlessly fracturing tree. It is an elegant escape. It dissolves the paradox completely, and it asks you to accept a price almost beyond imagining, infinite unseen worlds. Many worlds is breathtaking, but it is not the only answer, and it is not the one most working physicists reach for today. There is a quieter explanation, less metaphysical, more mechanical, that resolves much of the mystery without invoking consciousness or multiverses. It is called decoherence, and it begins with a humble observation. No quantum system is ever truly alone. Isolation, the perfect sealed laboratory of our thought experiments, is a fantasy that nature almost never permits. A real particle is bombarded constantly. Photons strike it. Air molecules collide with it. Stray fields tug at it. And every one of those interactions entangles the particle with its surroundings, leaking information about its state into the wider environment. The delicate interference between the particle's possibilities, the very thing that makes it quantum, depends on those possibilities staying private. The moment the environment learns the answer, the secret is out and the interference is destroyed. This happens with shocking speed. For anything larger than a molecule, decoherence unfolds in a fraction of a second, far faster than any eye could blink, any neuron could fire. The superposition is not waiting for a conscious mind, it is dissolving instantly into the thermal noise of the world, scrambled beyond recovery across countless particles. By the time the friend looks, there was nothing left to collapse. The world collapsed it first. And here is the subtle, beautiful twist. Decoherence does not literally collapse the wave function. Mathematically, the superposition is still there, just spread so thinly across the entire environment that the different outcomes can never again interfere or recombine. They are effectively sealed off from one another. The snap we imagined, that dramatic moment of collapse, was never a real event. It is an illusion produced by our inability to track the universe's tangled web of entanglement. This is how the solid, ordinary world emerges from the quantum fog. Decoherence explains why we never see cats both alive and dead, why detectors point one way, why reality looks classical the moment it gets large. The strangeness does not switch off at some mysterious threshold. It drowns continuously in the ocean of environmental interaction. The everyday world is not the opposite of the quantum world. It is a quantum world blurred by relentless contact with everything else. So return, finally, to our opening question. Does the universe exist when no one is looking? Decoherence offers comfort. Yes, the moon is there whether or not you glance at it, because the cosmos is endlessly observing itself, particle by particle. But it does not fully silence the deeper unease. Decoherence explains why outcomes look definite, not which outcome you specifically end up in. The hardest part of Wigner's question still lingers in the dark. One of the boldest thinkers of the century, the physicist John Wheeler embraced that unease rather than fleeing it. He proposed something he called the participatory universe. We are not, he argued, spectators peering at a finished world that sits indifferently behind glass. The act of observation is not passive. By asking questions of nature, by measuring, by looking, we take part in bringing the answers into being. Observation is a kind of creation. Wheeler imagines the universe as a vast, self-referential loop. Reality gives rise to observers. Observers look back and, through their observations, help give shape to reality. The present in his vision reaches back and lends concreteness to a past that was, until measured, only a haze of possibility. It is a strange and dizzying idea, a cosmos that is not simply out there, but woven in part from the very acts of attention we direct upon it. Whether or not Wheeler was right, the lesson of the last 100 years is impossible to unlearn. The observer cannot be cleanly removed from the description of the world. In Copenhagen, observation triggers reality. In many worlds, observation splits it. In decoherence, the environment observes ceaselessly on our behalf. Every serious answer to the measurement problem leaves a fingerprint of the observer pressed into the foundations of physics. We are not separable from what we see. That was Eugene Wigner's quiet, devastating gift back in 1961. He did not give us an answer. He gave us a wound that will not close. He showed that two careful observers applying the same flawless physics can arrive at contradictory accounts of what is real more than 60 years later. That paradox has not been solved, only sharpened, tested in laboratories, and confirmed to strike at the very meaning of an objective fact. Perhaps that is the most haunting thought of all. We are made of the same particles, ruled by the same uncertain equation, born from the same quantum fog as everything we study. And yet here we are, arrangements of atoms complex enough to turn and look back at the universe that made us. We are the cosmos observing itself. Whatever reality is, we are not outside of it. We are the eye it opened upon itself. So the next time you look up at the night sky, sit with the strangeness for a moment. The stars you see may be drawn into sharpness by the very act of your seeing. The universe may be less a finished monument and more an unfinished conversation, one in which you are a participant, not a witness. If this glimpse into the abyss unsettled and thrilled you, subscribe and keep looking. Reality may depend on it.